In the last lecture, we talked about descriptive statistics. Descriptive stats can tell us a lot of useful information about our data. We're able to describe what the data we've collected tells us about our variables in a concrete way. It's no longer, I think most people prefer pancakes to waffles, but now you can clearly state that in your sample, this many people preferred pancakes and that many preferred waffles. We have data, and we can say quite a bit about it just by looking at central tendency, mean, median, and mode, and at frequency and variation. But there are limits to descriptive stats. These calculations can only tell us what is in our data itself, the specific sample about which we gathered our information. Descriptive statistics don't tell us anything about data we don't have. They simply describe the data that we do. For many projects, this isn't an issue. In action and evaluation research, for example, your task may be to simply describe what's going on in the specific organization, community, or case that you're studying. If your research is focused less on determining correlations and causality and more on describing a particular set of cases, again, descriptive statistics may be more than sufficient. But sometimes our research requires us to make inferences about our data that go beyond just describing it. Let's say you conducted an experiment and found a difference in the mean on the post-tests between your control group and treatment group. Is that difference a real difference or just due to chance differences between the two groups? Descriptive statistics alone can't tell you that. Or maybe you see a difference between your treatment group score on the pre-test and post-test. Is that difference big enough to be meaningful? And remember all our discussions about the importance of external validity? If you're interested in generalizing your results beyond the specific set of cases you included in your study, then describing your own data is insufficient. You're going to need to know how to calculate the likelihood that your sample does represent your wider population, whether you did an experiment, a survey, or any other kind of large N study where you used a sample rather than a population. For this, we turn to inferential statistics. Inferential statistics allow us to make inferences from our data. We're not simply describing our data, but drawing conclusions about it and potentially about the wider population. Now, this isn't a course in statistics, nor is it solely on quantitative methods of analysis, so we are not going to dig into every possible calculation you could do. A lot will depend on the specifics of your project. So I'm going to focus on some of the more common tests that researchers use to analyze their data and get answers. Z-tests, t-tests, and a test called ANOVA. But before we get started, let's talk about null hypotheses, errors, and statistical significance so you know how to interpret the implications of your findings regardless of the tests that you run. Let's start with null hypotheses. To this point, we've been focused on hypotheses, how they act as a potential answer to our research question, how they're derived from theories, and how we build our research designs to provide tests for them. I'm now going to flip things on you a bit. When it comes to hypothesis testing, we're actually going to focus on the null hypothesis and not the hypothesis itself. We've spoken of null hypotheses before. They're a statement that no relationship exists between our x and y. Here, our null hypothesis becomes specific based on what kind of calculation we're doing. If we're doing tests for correlation, then our null hypothesis may stay pretty much the same. For looking at the difference between groups, our null will change to say that there's no difference between the groups that we're studying. The key here is to remember it's the null hypothesis we're actually testing. This should make sense. Remember, we're never setting out to prove our ideas, our hypotheses, right. Instead, we set out to disprove. But it's the null hypothesis we're trying to disprove. By rejecting the null, we know that there's something there to capture. If we find no difference between means or no relationship between variables, we say that we cannot disprove the null hypothesis or eliminate it from consideration, at least not right now with our current data and calculations. If we do find a difference or relationship, then we can say that we reject the null hypothesis. That doesn't mean we necessarily found the difference or relationship that we were expecting. It just means that something is there. Let's also talk about errors. It's possible that our sample is not representative of the wider population. With a different sample, we might have gotten different results. That can go two ways. It's possible that our analysis of our sample mistakenly tells us to reject the null hypothesis. That is, our sample indicates a relationship or difference exists that in fact does not. This is called a type 1 error. It's a false positive. The other thing that can happen is that we fail to reject the null because our results show us no significant relationship or difference. But that relationship or difference might in truth exist, and a different sample would show that. This is a false negative, and it's called a type 2 error. A type 1 or type 2 error is an issue regardless of the kind of sample method you use. Even with a perfectly drawn random sample, it's still possible to have a type 1 or 2 error just by chance. Chance can sometimes have odd results. Let's actually look at an example of how chance can be a strange thing. There's a board game called The Settlers of Catan that revolves around players rolling 2 six-sided dice. When you roll those dice, the single most likely sum is 7. It will occur almost 17% of the time. 6s and 8s are next at almost 14% each, and so on as you move away from 7 until you get to 12 and 2, each only about 3% likely to be thrown. This is important in the game because you get card-based resources based on how you've distributed your settlements on the game board. Roll a number that's found on the territory you settled, you get resources. If no one rolls that number, you never get resources, no matter how much you've developed that particular plot of land. I once played a game where not a single 6 was rolled the entire game. This is highly unlikely. 14% of the time, a 6 should be thrown, and the game is built around the high probability of both 6s and 8s being commonly rolled. All of my initial settlements were built on 6s. Needless to say, I lost that game. The sample of die rolls in that game was random. The dice were not, my friends assured me, loaded or weighted in any way. But the sample wasn't really representative of what we would expect in the course of a game. It was a fluke. In every other game that I've played, the percentage of 6s rolled tended to be fairly close to what would be predicted. If I assumed that my odd game of Settlers was representative and ran tests using it, I'd be making type 1 and 2 errors all over the place. So even if you sample properly, there's still a risk of having an unrepresentative sample. Luckily, with a random sample, we can estimate the likelihood of that happening. So statistical significance is also important in quantitative analysis. Remember, we operate in a world of uncertainty in research, and we're rarely 100% certain of anything. This is particularly the case when we're dealing with samples and not populations. Our tests of significance are going to tell us how likely it is that our results are due to chance, rather than representing the real value for a population or due to some kind of error. Estimating statistical significance, frequently represented by p-values, will tell us how confident we should be in our results. The benchmark in most research is the 0.05 level. This means that there are only 5 chances out of 100 that your results are due to chance. Anything higher than that, and your results will generally be considered statistically insignificant. Basically, the risk of a false positive, a type 1 error, is too high. Lower than 0.05 and you're fine. We're almost ready to dig into our tests, but first let's talk about assumptions. Most of our statistical models rely on assumptions, things that we assume to be true about our data. Without those assumptions, our models won't work or will spit back results that simply aren't true. One reason to run descriptive statistics on your data before moving on is to check some of these assumptions. For example, many models rely on the assumption that your data was distributed in a particular way, perhaps normally distributed. We learned in our last lecture that in a normal distribution, the mean, median, and mode of your data are the same. If you try to run an analysis that assumes you have a normal distribution when your distribution is not in fact normal, your results are not going to be reliable. The standard ANOVA test, for example, assumes that your distribution is normal or at least quite close to it. Likewise, we often rely on the assumption of a linear relationship between our variables. Remember when we studied hypotheses and we learned the template of saying that there is a positive relationship between x and y? A positive relationship means that as x increases, y increases, and vice versa. That implies a linear relationship, that a unit increase in x leads to a unit increase in y, and that this doesn't change if x is at a low value or a high value. But not everything we study is a truly linear relationship. Take the relationship between age and height. For most people, they see relatively rapid growth at young ages and then a flat line for most of adulthood, with perhaps a slight decline in height at older ages. That is decidedly not a linear relationship, and we need to be aware of that when we reach the analysis stage and are picking our tests. Okay, we're ready to do some calculations. We're going to look at 3 important tests today: z-tests, t-tests, and ANOVA. Let's start with z-tests. Z-tests let us see if a sample score is statistically different from a known population score. In the case of my Settlers of Catan game, it would tell me if the average die roll in my losing game was typical or not. That could be the difference between me saying, I'll never place a settlement on a 6 again, or accepting that this particular game was a fluke and that settling on 6s is actually a decent strategy most of the time. For your research projects, this is valuable anytime you know something about your population of interest and want to see if a particular sample matches that population or deviates in some way. For example, perhaps you know how a particular group of students or trainees generally performs on a test, and you want to see if a particular set of student scores are representative of that expected performance. Now, you might think immediately that you don't need to do a calculation to know that. If the typical student average is a 75, for example, and this group scores an 80, then obviously they've done better. But remember, this is just one sample. It's possible that 80 is well within the range of an expected average. It's also possible that this is not within the range, that this set of students scored unusually high. Calculating z will tell us this. To do this, you need the mean of your sample, the size of your sample, or n, the mean of the population, and the standard deviation of the population. Use a standard stats package or spreadsheet program to do the actual calculations. A z-value tells you the number of standard deviations the sample mean is from the population mean. Let's say that in our testing example, our n is 40, the sample mean is 80, the population mean is 75, and the population standard deviation is 10. Our z-value is 3.16. This would fall outside a normal range. Remember from our discussion of z-scores that about 68% of cases fall within 1 standard deviation from the mean, 95% of cases within 2 standard deviations, and more than 99% within 3 standard deviations. Our result of 3.16 is outside that range, and therefore would indicate that our sample mean is not representative of our population. In this case, it would mean that this particular set of students scored significantly, statistically significantly, higher than expected. If the difference in means had been just 3 points, with the sample scoring a 78, then the z-value would be 1.9, within the 95% of cases that might be expected. That's just a 2-point difference in scores, which might not seem like much, but it's a statistically significant difference, and that can be important to know. Z-tests are great and are a useful thing to do at the start of your analysis, but there is a limitation. You need to know the standard deviation of your population. If you don't know that, you'll want to use a t-test instead. You can use a t-test when you want to know if your sample score is statistically different from your population score, but you don't know the standard deviation of the population mean. This is called a one-sample t-test, and it's very similar to the z-test. The main difference from a z-test is that we use the standard deviation of the sample rather than that of the population. Every other calculation is pretty much the same. Once you have your result, you then use a t-distribution table to determine the critical value for t. This is the value that your t-value essentially has to beat to determine statistical significance. If your t-value is higher than that listed under your chosen level of significance, then the difference between the two means is significant. If not, it's, well, not. You can find a t-distribution table online through a basic internet search. T-tests are also commonly used anytime you want to compare the statistical difference between two groups. And we're going to focus on this application. Descriptive statistics can tell you the average performance of each group on your dependent variable. If you want to know whether or not that difference is statistically meaningful, then you'll want to use a t-test. That means anytime you're comparing a control group and a treatment group, as in our two-group experimental designs, both those with and without pretests, you'll probably want to use a t-test. It's also useful if you're comparing programs in evaluation research. There are two commonly used types of formulas. One is meant for unpaired groups, that is, two separate groups with separate scores, such as a control group and a treatment group. Paired tests are meant for when you're comparing multiple measures from the same group, such as a treatment group that has taken a pre- and post-test. You can calculate this by hand, but again, you are better off using a stats package that can easily do the t-test for you. You just need to know whether you want to use a paired or unpaired test. However you make the calculation, you're going to get a number that's called the t-value. This tells you the ratio of the difference between the two groups to the difference within those groups. The larger the number, the more the groups are different from each other. So if for example, you're working with an unpaired treatment and a control group, then a higher number would mean that there's a larger difference between your treatment and control groups. So you want to see large t-values when you run this test if you hope to disprove your null hypothesis. A smaller t-value would instead confirm the null hypothesis. So how big is big enough? Well, that depends on your sample size. The smaller your sample, the larger the t-value needs to be. To know specifically how big the t-value needs to be for your sample, we have to check it for its statistical significance. Most stats programs will tell you the statistical significance of your t-value when you do the calculation. This takes the form of a p-value. Sorry about all these letters. I promise I didn't name them. You'll look for the p-value in your statistical output, and you want to see that it's less than 0.05. Remember, that's our standard level of significance. A p-value of 0.05 means there's no more than 5% likelihood that our results are due to chance. That means it's a 95% likelihood that our results are a real result. You can also use a standard significance table online or in the back of any stats textbook once you have your t-value. What does this mean in practice? Well, if you were comparing a treatment and a control group, this means that any difference you found in the post-test means between those two groups is probably real. That would indicate you could reject the null hypothesis. What doesn't this mean, though? It does not mean that you've proven your hypothesis correct. Remember, we rarely use the word prove in research. There's still a 5% chance that your results are due to chance, so you can't be 100% certain that you've got it right. You've definitely got something, evidence in favor of a likely difference, but don't overstate your claims. We also have to keep in mind that if there are any internal validity issues with our study, that these may account for our results. That's why we account for these possibilities when discussing your results. Quantitative analysis lets us state specifically how likely it is that our findings are valid. That leaves room for exceptions, nuance, and restrictions, and it means we're being honest about the scope of our claims. That allows other researchers to build on what we found, and over time will increase confidence in the breadth and scope of our answers. When you remember that your work is part of a larger story and that any findings move us forward in the narrative, it's easier to accept the limitations of what we can say about our claims. And it's dangerous to do otherwise. Already, research is bent and shifted and manipulated to fit the stories that others want to tell. The defense we have against this is to point back to the original work and note the restrictions and conditions. There is an honesty there that we can use to fight back against any manipulations of our findings. But if we participate in that manipulation from the beginning, then we're no longer in the business of finding answers. We're back on the quest to prove ourselves right, and that's not good research. So keep this in mind as we talk about different statistical tests. We'll consider statistical significance pretty regularly, and it's crucial to keep in mind why we do this. One final point on t-tests. If you look at a critical values table, you'll often see different values for a one-tailed test and a two-tailed test. Which you use depends on whether or not you expect the difference between your groups to occur in a particular direction. If your hypothesis expects to find that one group will have a higher mean than another, then you might want to work with a one-tailed test. That means that you expect any extreme values to occur solely on one side of the distribution. A two-tailed test indicates that you're testing for a difference, but you don't know if it'll occur at the high end or low end of the distribution. Your hypothesis expects to find a difference, but doesn't indicate the direction of that difference. Most of the time, you're probably using a two-tailed test, but you might use a one-tailed test under certain circumstances. For example, if you're looking at the scores of your trainees on their test, you may not care if they do significantly better than previous cohorts, but only if they do significantly worse. In such cases, you might use the one-tailed test. It may seem like a small point, but it changes the critical value needed for statistical significance. So as always, keep your hypothesis and null hypothesis in mind when choosing your test. That's enough for now on t-tests. Now let's talk about analysis of variance, or ANOVA. This is a test that's really useful for experiments and survey research. Like a t-test, ANOVA lets you compare differences between groups to test for statistical significance. In fact, a one-way ANOVA test is functionally equivalent to a t-test, although it looks at differences in variance rather than difference in means. The one-way ANOVA test works with only one independent variable with two values, which are referred to as levels. So if we were testing Jane Elliott's students in her experiment that used eye color to study discrimination, we could use ANOVA. We would take the scores of the students on their reading tests as our dependent variable, and the independent variable would be whether or not the student was in the discriminated against group that day. That's one independent variable with just two levels, member of the discriminated eye color group or not. The two-way ANOVA test gives us a bit more power though, so we're going to focus on that. It lets you examine two independent variables, each of which can have multiple levels. Recall the Good Samaritan study we discussed during our lecture on quasi-experiments. The researchers were interested in factors that affect whether or not someone would help a person lying in an alley in clear need of aid. They studied two situational variables, whether or not the participants were in a hurry to deliver a talk and what kind of talk they were mentally preparing for, either one based on the Good Samaritan parable or one on careers for seminary students. The authors did an analysis of variance tests to look at the role of these two independent variables on the dependent variable of type of aid offered to the victim in the alley. One variable, the type of talk, had two levels, and the other, the hurry condition, had three, low, intermediate, and high level of hurry. The ANOVA test, therefore, lets you do statistical analysis when your independent variables are at the nominal and ordinal level of measurement, and your dependent variable is at the interval or ratio level. So if you're working with variables such as gender, race, marital status, or other traditional categorical variables, and you want to compare group differences, the ANOVA test may be a good choice for you, particularly if you have more than 2 or 3 independent variables. When you run an ANOVA test in your stats program, you're going to get what's called the F value for each variable, as well as the interaction between each pair of variables. The F value is similar to the T value from the t-test, but the t-test only tells us about the differences in a single independent variable, while this F test will give us information about more than one variable at a time. So how do we interpret our results? Well, we have to do 2 things. First, we need to find the critical value of F using a table. This will give us a benchmark to judge our results. If our F value is less than the critical value in the table, we should accept the null hypothesis. Only if the F value is greater than that critical value can we consider rejecting the null hypothesis and move forward. In a critical values table, you have 2 sets of degrees of freedom. Degrees of freedom is a term used for the number of independent pieces of information in our calculation of our estimate. It's generally easy to calculate. It's basically the number of pieces of information minus the number of estimated parameters, which is often 1. Frequently, our pieces of information is our number of cases, or n. So in many cases, our calculation of different degrees of freedom would simply be n minus 1. For the F table, we'll need 2 different degrees of freedom. One is the degrees of freedom for the number of categories in your variable, and the other is the degrees of freedom for the number of cases in the variable. If you look for the number at the intersection of those 2 degrees of freedom, that will give you your critical value, and we want our calculated F value to be higher than this critical value. If our results pass this test, we still have one more step. We have to see if our results are statistically significant. So look at the p-value that your stats program gives you after doing the test. You'll recall from earlier that the p-value is the term we use for the likelihood that our results are due to chance, and we usually want this to be 5% or less. So if your F value is higher than the critical value from the table, and it has a p-value of 0.05 or below, then you can probably reject the null hypothesis. You've found a difference between groups. Which groups, we don't know. There are a few additional tests you can do to determine that. But for now, though, this is an important finding that may provide you with an answer to your research question. If your p-value is above 0.05, we can't reject the null hypothesis, even if your F value was higher than the critical value. In such cases, we can't say that there's a statistically significant difference between our groups, even if the difference in numerical terms appears large. Keep in mind about what we learned earlier about type 1 and type 2 errors. We may reject our null hypothesis because we found that our F value was high enough and it was statistically significant. But even if this is true, it's still possible that we made a type 1 error and we've mistakenly rejected the null hypothesis. There might have been sampling error. That means that our sample doesn't actually reflect our population. We can have the strongest results ever, but if our sample is unrepresentative of the population, then ultimately our results are limited in their scope. Well, we can't be sure that we've avoided a type 1 error. We can estimate how likely it happened thanks to calculating statistical significance. ANOVA is a commonly used procedure, but keep in mind that our discussion here has been necessarily brief. There are variations on the procedure based on how many variables are involved and whether or not you're comparing 2 completely different groups or the same group over time. Your stats program should have the option to do all of these. We're not done with inferential statistics by any means. In our next 2 lessons, we're going to dig deeper into more tools of quantitative analysis. Our discussion won't be exhaustive, but hopefully you've already seen several applications that might apply to your own projects. Next up, we learn about testing for correlation and causation between 2 variables.